Hello, today we're going to be discussing electromagnetism and how that applies to electric motors and how it makes electric motors spin. When I apply 3 volts of electricity to this middle airsoft electric motor, it spins. We're going to discuss what is in this motor that makes it spin and how applying electric current to it makes it spin. Within an electric motor, we have 3 major parts. First, we have this end bell, which holds these 2 brushes that consistently push up against the commutator in the inside. This is the brush. When we remove the end bell, we have a commutator, which is attached to individual armatures. These armatures are then surrounded by a neodymium magnet, and when we apply current, the motor spins. But let's understand how that works. In order to understand electromagnetism, we need to understand the right-hand rule, or the second right-hand rule. The second right-hand rule states that when we have a wire in which the current is flowing from one side to the other, it creates a magnetic field that circles the wire. This can be shown by taking your hand, putting your right hand, putting your thumb in the direction of the current and wrapping your fingers around the wire. This represents the magnetic field. It can also be represented by an arrow in which the feathers of the arrow are into the page and the tip of it is coming out at us, wrapping around. Wrapping around. In order to see how the second right-hand rule applies to electromagnetism, we have a wire wrapped around a screw. If we run current from one side to the other, we now have an electromagnet created. This is because at this point here, current is wrapping around this way, so it's not too strong. But with each of these that are wrapped vertically, it is aligning a massive amount of magnetic field in one direction or the other as it continues out the other side. This will polarize this screw, making it a magnet. When we add 2 more magnets to the equation, we have a south side of the electromagnet and a north side of the electromagnet that want to continuously stay with this magnet. When we actually switch these 2 poles, or these wires, it switches the poles of the electromagnet by switching the direction of the flow of current, making the electromagnet switch directions, forcing it to spin. If we were to continue switching it back and forth, the electromagnet in the middle would continuously spin over and over and over. That is the basics to how electromagnets work. So now, if we were to replace this here screw with an armature instead, essentially one big wire, we would have the inside of a modern day electric motor. Because the wires would get tangled if they were to keep switching over and over, we have a commutator separated in half or in as many parts as there are armatures, in which brushes are pushing on it from either side, sending current through the commutator into the armature and out the other side. As the commutator and the armature spin in the middle, the brush will continuously push against it as it switches from each state. This can be seen in that motor that I showed previously, where as the armature in the middle spins with the commutator, the brush will push on it, and with each time that it meets a different section, a different electric magnet will be activated. The more armatures there are within this motor, the more electromagnets are created, and the more that the brush will power as it spins. So as the motor spins from a point of maximum torque to a point of minimum torque, the electric magnet will continuously want to keep setting itself up with its satisfied pole, meaning that the southern pole will meet the northern pole, and the northern pole of the electromagnet will meet the southern pole of the neodymium magnet. As I said earlier, each one has a maximum torque of 90 degrees. This is where the armature is 90 degrees to the magnetic field, and this is when it is 0, and we have 0 torque. The amount of torque that is created can be represented by this equation, in which torque is equivalent to the number of turns times the current times the area times the magnetic field times the angle normal to the magnetic field. When this angle is 90 degrees, sine will be equivalent to 1, and it will be negated. So maximum torque is this equation. In order to understand how much current is being drawn to a magnet, we need to understand current. In the equation, velocity equals IR, I equals current. We can rearrange this so that the current is equivalent to the voltage divided by resistivity. Unfortunately, we do not understand the resistivity of this motor either. However, we do know that there is copper wire in here. The resistivity of copper wire is equivalent to the length of it times the electrical resistivity divided by the cross-sectional area. When we rearrange this equation, we can plug this equation in for R here, and in turn, put that in for there. In this case, we applied 3 volts of electricity to the motor, and the electrical resistivity of copper is 0.0171 ohms times meters squared millimeters squared divided by meter. Unfortunately, we do not know the number of turns or the gauge of the wire and so forth. However, if we did know that, we could solve the maximum torque. When looking at torque, we know that this can be represented by a sine wave. This is because, like I said earlier, the armature oscillates from a position of maximum torque to no torque, in which the angle normal to the magnetic field running from one direction to the other is 90 degrees is maximum torque. And when it is 0 degrees, there is no torque. That is seen right here, at which it is 0 degrees, 90 degrees, back to 0, negative 90, and 0. If we were to have this magnet and we applied the second right-hand rule to it again, however in a different context, in which we turn the pinion gear of this motor, we could actually create a magnetic, or not a magnetic field, a current, because of the electromagnet in the middle. If we induced an electromagnet in the middle and we began to turn this current, because we have a magnetic field rotating and oscillating, we would instead create a current that could come out the other side.